Now, we will be discussing on various models and application. There actually we will be discussing the design aspect. Okay. In membrane operations, we generally discuss the few models like osmotic pressure model, then gel polarization model, then resistance in series model, solution diffusion model, Hermias pore blocking model. There are so many other models also. So, we will be discussing a few of these. The main objective of these models is that the effect of concentration polarization can be quantified using these models, and flux decline profile, then concentration of the solute in the permeate can be predicted, or we can say this one, if we want to design a membrane module or membrane reactor, then we need to do the theoretical studies. First, we will be discussing on osmotic pressure model. The definition is saying that we will be considering this resistance due for the separation in terms of osmotic pressure, because we know that for the as per the Darcy's law, the driving force is del p minus del pi. There with time this del pi goes on increasing, where the solute concentration is more, then osmotic pressure is very less, but where the solute concentrations are less, their contribution of the osmotic pressure is there. So, we will be discussing now this osmotic pressure model. So, first we need to do the assumptions like this assumptions. One is that we can say this concentration boundary layer is fully developed. And say C actually is not the function of C in y axis. We will be discussing what is that in y axis, and delta, that is also not the function of, we can say, delta in the y direction. Means if we say this is, you can say this in z direction, say suppose fluid is flowing, and y is this, we can say this in the radial direction. Let us take this membrane like this material. Okay. So, then say flow of the permeate will be like in the beginning, the solute as well as solvent will be moving towards this membrane, and then we can say Jw actually will be getting that whatever the permeate flux, and say concentration of the solute will be Cp, and say that is which will diffuse back to this bulk. Suppose this part is bulk and this part is permeate side, and this is membrane. So, which will go back to this bulk, that is we can say this one d dc dz. Okay. So, that amount actually will be going back to the bulk again, and say we can say this one, say we assume that the concentration boundary layer is fully developed. So, we can say the concentration profile will be like this, and say if we say z is in this direction. So, the bulk concentration will be like this, which we can say this one concentration of the solute in the bulk in the beginning. So, this is we can say bulk, and whenever this entirely developed system, so then we can say the total concentration will be, that is we can say this one Cm, that is membrane surface concentration. The Cm will be like this membrane surface concentration. So, we can see the solutes will be deposited like here, and then say this way whatever this we can say this one the thickness of the solute will be developed like this, we can say that is delta. So, now we can say this one feed is we can say directing towards this membrane surface, and then permeate flux is obtained and solute concentration in the permeate is Cp, and we can say this one back diffusion of the solute to the bulk. So, at the steady state we can say that is minus dC dz. Okay. So, now we can say this one we at steady state we can say, so whatever the flux values are entering and which is exiting. So, we can say from there we can say this summation of the flux value will be 0. Then say what is we can say this one entering, suppose this flux is there with concentration at any time, we can say this one is C. So, Jw into C, and what is exiting, that is we can say this one Jw into Cp, and which is going back minus dC dz. So, minus dC dz d dC dz. So, that will be equal to say 0. Okay. So, this is at the steady state we can say this one this is say entering and these two are exiting like this. So, that way we can say this one whatever is entering and these are exiting. So, from there Jw into C minus Jw into Cp plus d into dC dz is equal to 0. Okay. So, from here we can say dC by say C minus Cp is equal to minus dC minus Jw by d into we can say dz. Okay. So, that is we can say just by we can say this one manipulation. Now, we say if we take this boundary conditions, if we say for this type of say membrane operations, suppose z is equal to 0. So, here actually z is equal to 0, that time we can say C will be Cm, means this is the membrane surface concentration, and when this is fully developed, so we can say this one Z is equal to delta, there C will be this bulk concentration, means after this delta whatever the concentration is there, means delta thickness is developed due to this membrane operation, and that is why in the membrane surface the solute concentration is maximum, that we say membrane surface concentration, and at the bulk when there is no effect of this we can say the thickness delta, there C will be Cv. Now, we will be doing this one, we will be integrating this one, say from we can say this one Cm to Cv, and if we integrate this one Cm means Z will be 0 to delta. So, from here we will be getting say if after integration we will be getting this one, say Jw will be equal to d by delta into ln Cm minus Cp divided by Cv minus Cp. So, that actually we are getting just by integrating the previous equation. From here we will be getting this, if we integrate this equation we will be getting this Jw, or we can say ln Cm minus Cp by Cv minus Cp, that will be Jw by d into delta. From there just after manipulation we will be getting Jw is equal to d by delta, and this d by delta we know this is mass transfer coefficient. Okay. So, k ln Cm minus Cp by Cv minus Cp. Okay. So, this is we can say k is the mass transfer coefficient. Okay. Now, we will be doing just manipulation in this equation like this Cm minus Cp by Cb minus Cp, that will be equal to say Jw by k, the say it will be like a exponential of Jw by k, just keeping this one and taking the anti-logarithm. Okay. So, now we know another thing, just we can say we will take RR, that is real retention, is equal to 1 minus Cp by Cm. Okay. So, from there we can say this one RR into Cm is equal to Cm minus Cp. So, here we can put one thing, so we can put this Cm minus Cp as RR into Cm. So, there actually we can say put here, that is RR into Cm by Cb minus Cp is equal to exponential Jw by k. Okay. So, RR into Cm is equal to say Cb, this is RR into Cm, we will be getting as like Cb minus Cp into exponential Jw by k. Okay. And then say if we manipulate this this equation, then we will be getting say Cm is equal to we can say Cb into exponential Jw by k divided by RR plus 1 minus RR into exponential Jw by k. So, just by manipulating this one we will be getting this Cm. Cm is equal to, or we can say this one we explained this one in the beginning, that Cm actually membrane surface concentration cannot be measured directly. So, there we can measure indirectly. So, from this equation we can say the Cm, or we can say membrane surface concentration, can be measured using these known parameters. Okay. And here we also explained that if the solute molecular weight of the solute is very small, then osmotic pressure has the contribution, and we know this as per this Van 't Hoff equation. This with the progress of this membrane separation process, the osmotic pressure going on increasing. Okay. So, here we can say this one, this Van 't Hoff equation is applicable here. So, there we can say this one pi is equal to say RT by m into C, that we can take as, we can say this one, this term as say we can say B into C we can say, and so then delta pi will be, means say with time what will be happen, that will be say pi, that is Cm minus pi will be at Cp. So, that difference will give the osmotic pressure gradient. So, with time what will happen, the resultant driving force will go on decreasing, as these driving force is delta p minus delta pi. As this delta pi is going on increasing, so this driving force, we can say this one driving force will go on decreasing, because you see delta p, whatever the transmembrane pressure drop, that is what is applied, that will remain constant for the entire process. So, we can say that with time the we can say effective driving force will go on decreasing. Okay. So, that is nothing but we can say this one B into Cm minus Cp. Okay. So, that is we can say this one again we can get this one Cm minus Cp we can take is equal to B into Rr into Cm. So, we have this delta pi is equal to this one. Now, we can say this we know from Darcy's law, we know that Jw this is we can say the water flux is equal to this Lp into del p minus del pi. Okay. So, that will be nothing but Lp into del p minus B into Cm into Rr. Okay. So, now we can say this one will be putting these values of Cm and Rr in this equation. Suppose putting the values of Cm and Rr. So, we can get this Jw, this water flux or permeate flux value will be Lp into del p minus B into Cm into R, that is we can say B into Cm whatever we have obtained from this previous equation. Cm is equal to Cb into exponential Jw by k by Rr plus 1 minus Rr into exponential Jw by k. We will be putting here B into Cb into Rr into exponential Jw by k divided by Rr plus 1 minus Rr into exponential Jw by k. Okay. So, from here actually we can say and say Jw is equal to, then we have Lp into del p minus B into Cb into Rr into exponential Jw by k by Rr plus 1 minus Rr into exponential J by k, where B is taken as this R T by m. Okay. So, that is the we can say this one expression for Jw, and say we can say now we can do one thing, that Cm is equal to, from this we can say just by manipulation we can get again Cm is equal to Cb into exponential we can say Jw by k divided by Rr plus 1 minus Rr into exponential Jw by k, and from there this we can say this Cm by Cb will be this one, that is we can say this one exponential Jw by k by Rr plus 1 minus Rr into exponential k. This Cm by Cb, that is we can say this ratio is called as that concentration polarization modulus, concentration polarization modulus. So, Cm by Cb that can give one measure of the osmotically controlled system. Like if we say that if Cm by Cb is very high, then we can say that membrane surface concentration of the solute is much more higher compared to this lower one, or there we can say this one flux value will go on decreasing, or we can say this one Rr value will go on decreasing, and we can say with k value it will go on increasing. So, we can say Cm value Cm by Cb, so that will we can say this one that increases with Jw this Rr and decreases with you can say this one k value. Okay. Now, we need to understand these mass transfer coefficient values for this case actually, this whatever the k value actually we need to get. This is very simple, we can say this mass transfer consideration we need to this one explain mass transfer coefficient consideration. So, suppose if we say if it is in laminar flow regime, then so we can say this one if it is conduit flow. So, there we can say this one Levick relation will be we need to follow, like we know this one Sherwood number is equal to 1.86 into Reynolds, Smith and d by L to the power 1/3. Okay. So, where d is the we can say this one equivalent diameter of the channel. Okay. So, from there we can say this one using we need to follow this correlation, means where laminar flow regime say Reynolds number is less than 2100 and we can say this one it is if it is in the conduit flow. So, if it is in the say in laminar flow, if it is in the we can say tubular flow condition. So, Reynolds number will be the Sherwood number will be equal to say k d by d, that is equal to 1.62 into Reynolds, Smith and d by L to the power 1/3. Okay. So, when it is we can say this turbulent flow regime, if it is turbulent flow regime, then suppose Reynolds number is greater than 4000. So, then we have this Sherwood number is equal to 0.023 and Reynolds number to the power 0.8 and Smith number to the power say 0.33. So, that is we can say this is like say Ditas-Boelter type equation. Okay. So, now actually we will be considering some simple cases, like say we can say we will take this first step, like we will be discussing now case 1, where we can say this one no concentration polarization. Suppose there is a condition where we can say case 1 no concentration polarization. So, there we can say this no concentration. So, Cm will be almost equal to we can say this one Cb, means say the solutes are not deposited on the membrane surface and in the entire membrane separation process the solute concentration remains almost same at the membrane surface. Okay. It can happen when the stirring speed is very high. So, this is we can say this one stirring speed is very high. So, in that case we have this ln Cm minus Cp by Cb minus Cp will be equal to Jw by k, that will be equal to say if we put Cm is equal to Cb, then it will be like 1. So, that time we can say this one 0. Okay. So, in that case we can say this one so this Jw, then that case will be Jw is equal to Lp into del p minus B into Cb into this one Rr. Okay. So, in that case we can say whenever this there is no concentration polarization, that time Jw will be Lp into del p minus Cb into Rr. Okay. In another case, suppose if we say case 2, where we can say this low polarization modulus, the low polarization condition, suppose for low polarization condition, suppose say applied pressure is low, then we can say Cb is low, or say we can say this one bulk concentration or feed concentration is very low and say high turbulence. So, in that case we can say this one, if turbulence is very high, means this K will be this one very much greater than Jw, or we can say this one mass transfer coefficient value will be very high. So, for that case, this we can say, in that case the ratio Jw by K will be say lower than 1, and say we can say this one, in that case say ln the exponential Jw by K, that is we can say this one can be expanded as 1 plus Jw by K. Simply we can write this one. Okay. Now, we will be putting this one in this expression for Jw. So, in that case Jw will be equal to Lp into del p minus whatever the expression for del pi that was there, in terms of we can say this one B into Rr into Cb into exponential Jw by K will be converting now is equal into 1 plus Jw by K divided by say Rr plus 1 minus Rr into exponential Jw by K will be replaced by 1 plus Jw by K. So, now we can say this one. So, this will be the expression for the flux permeate flux value. Okay. Now, say if complete retentive membrane is there, suppose if this complete retentive membrane means we can say this one. So, that time we can say this one, whatever the feed is there, no solute will be passing through the membrane, the entire solute is retented, then Cp will be equal to say 0, and say this one Rr will be 1 minus Cp by Cm, that will be 1 minus 0, means Rr will be 1. So, in that case this Jw will be say we will take Lp into del p minus B into Cb into 1 plus Jw by K. Okay. So, in that case would be, that will be say we can say Lp into del p minus Lp into B into Cb into, we can say just by this we need to do the manipulation, B into Cb minus Lp into B into Cb into Jw by K. Okay. So, from there we can say this Jw will be equal to, just after manipulation will be del p minus B into Cb divided by 1 by Lp plus B into Cb by K. So, this is the, we can say this one expression for permeate flux, if we can say Rr is 1, but this is not realistic. So, realistic approach is not that Rr should be 1, it should be sometimes less than 1, or we can say the 0.999 like this, but Cp in most of the cases Cp will be near to 0, but may not be 0. Okay. And say in this case we can say, we can write this way, ln Cm minus Cp by Cb minus Cp is equal to Jw by k, that we got from this. We can say this one from the very basic, we can say this one flux analysis. So, then we will be just putting this Cm minus Cp value there in terms of Rr. So, it will be like this, ln Cm into Rr divided by Cb into, we can say R 0, that will be coming as Jw by k, because we know that Rr is equal to 1 minus Cp by Cm, whereas observed tension is equal to 1 minus Cp by Cb. From these two equations actually we will be getting that ln Cm into Rr by Cb into Rr, just by getting this these two values actually from this equation we will be getting like this, or in terms of 1 minus say R 0 or 1 minus Rr, because is Cp by Cm and Cp by Cb. So, here also we can say, from here we will be getting in terms of say Cp by Cm is equal to 1 minus Rr and Cp by Cb is equal to 1 minus Ro. So, from here we can do the manipulation like this, ln into 1 minus Ro into Rr divided by 1 minus Rr into Ro is equal to Jw by k. Okay. So, from here actually we can say ln Ro by 1 minus Ro is equal to ln Rr by 1 minus Rr plus Jw by k. So, now we have this linear expression for observed retention, real retention, flux value and mass transfer coefficient. Okay. So, now we can do one thing, say this from experimental results, suppose this from results we can get this Jw and Ro. So, we can get, say we can get this one, this will be known. Now, we will be plotting this, we can say this one ln Ro by 1 minus Ro with Jw. So, we will be getting this, suppose the expression is ln Ro by 1 minus Ro, that is y is equal to ln Rr by 1 minus Rr plus Jw by k. Okay. So, as we will be plotting this one, so we can say this one intercept actually we will be getting, this is nothing but this is say intercept will be C, that is say we can say from here we will be getting I is equal to ln Rr by 1 minus Rr, and this slope will be 1 by k. Okay. So, we will be getting this intercept and slope, and from there we will be getting what will be the real retention value and what will be the mass transfer coefficient. The inverse of the slope will get this, will be giving the mass transfer coefficient values. Okay. Now, we will be solving a simple problem like this, an enzyme is being concentrated in an ultrafiltration module with feed in a cross flow cell. Under the given flow condition, mass transfer coefficient at a membrane surface is estimated to be 3 into 10 to the power minus 5 meter per second. Bulk concentration is 0.3 mass percent. If the water flux is 0.41 meter cube per meter square hour, calculate polarization modulus, that is Cm by Cb, and the concentration of the enzyme on the membrane surface, that is CM. The membrane has a distribution of pore and 95% rejection, that is we can say this one retention is equal to 0.95. If the diffusivity of enzyme is 8 into 10 to the minus 7 centimeter square per second, calculate the thickness of the mass transfer film. This we can say delta. So, we need to get Cm by Cb, then Cm, then rejection is given, then we need to get delta. So, these values we need to get from the this one, we need to solve this problem. Now, we will be solving this one very simply, we can solve this one. Whatever the given this one values are there, we will be writing now in the beginning. Say suppose Jw, that is given as 0.41 meter cube per meter square hour. Then H is given as 1.139 into 10 to the power minus 4 meter cube per meter square hour. Then R is given as 0.95 and mass transfer coefficient is given as 3 into 10 to the power minus 5 meter per this second. Okay. Now, say we need to find first say polarization modulus. That is Cm by Cb. So, we can say this one Cm by Cb is equal to, we can say exponential Jw by k by Rr plus 1 minus Rr into exponential Jw by k. So, that is given as exponential Jw is equal to 0.41. So, Jw is equal to, actually this is 1.139 into 10 to the power minus 4 by k is equal to 3 into 10 to the power minus 5 divided by Rr is equal to 0.95 plus 1 minus 0.95 into exponential 1.139 into 10 to the power minus 4 divided by 3 into 10 to the power minus 5. So, it is coming out as, say the value is 14.02. So, we can say the Cm by Cb is equal to 14.02, or we can say this one, the solute concentration increase in the we can say in this membrane unit is done by 14 times. Okay. Now, we need to get this Cm is equal to, say we can say this Cm is equal to say 14.02 into that Cb is equal to say 0.3 mass percent, we can say 0.3 mass percent. So, it is coming out as 4.2 mass percent. Now, we say delta is equal to d by k. Okay. So, that is you can say this d value actually is given as 8 into 10 to the power minus 7, d is given as 8 into 10 to the power minus 7 centimeter square per second. So, that is we can say 8 into 10 to the power minus 7 by 3 into 10 to the power minus 5, 10 to the power minus 3, say in terms of meter we can say 10 to the power minus 3, it will be like this in centimeter. So, it is coming out as 2.6 into 10 to the power minus 4 centimeter. Okay. So, we can say this one thickness is 2.6 into 10 to the power minus 4 centimeter, this one thickness will be generated. Okay. Next, we will be discussing about the gel polarization model. Okay. So, in gel polarization model there are assumptions also. When this membrane surface concentration exceeds the solubility limit of the solute, then phase separation takes place and gel layer actually is formed on the membrane surface. So, for very high molecular weight solutes, osmotic pressure is negligible, because we know that as per this Van't Hoff equation, the molecular weight is there at the denominator. So, you can say the osmotic pressure value will be very less. So, osmotic pressure controlled zone is compressed, and we can say this one primarily it is gel layer controlled. So, there we can say this one, we can use this film theory like this, say Jw will be equal to K into ln into Cm minus Cp by Cb minus Cp, that is nothing but delta P minus delta pi, that is driving force, by mu into Rm plus Rg, where this Rm actually we can say this one membrane surface concentration and Rg is equal to the gel layer resistance. Because you see in the case of these high molecular weight compounds, there is a tendency of gel formation over the membrane surface, and that is why the resistance value is going on increases actually with time. That Rg, that is the function of, we can say this one, time. So, gel layer is assumed to behave like a solid, so we can say this one, that is why it is giving additional resistance. Like membrane resistance, that is the intrinsic property of the membrane. So, it gives the resistance for the transport of the solvent through this, and when this gel layer will be formed over this membrane surface, that is we can say this one it is like a dynamically formed membrane, and it gives the additional resistance. So, permeate will not contain any solute, say we can assume that as this it is giving a new we can say the layer, and the solutes will be trapped on this, that is why say no solute will be permeating through this membrane, and that is why Cp is assumed to be as 0. So, then we have this Jw is equal to K into ln into Cg by Cb. Now, we will be solving this one, say for this gel polarization model, we will be deriving this equation for this permeate flux value. Okay. Suppose we have this membrane again, and Jw is this, we can say this one flux of the, we can say the solvent is there towards this membrane, and say Jw whatever out of the solvent is this, and Cp, that is we assume that it is will be equal to 0, but for the timing we are keeping this one, and the back diffusion that I told this one, that will d, dc, dz will be there, and here in this z direction, suppose this gel layer or thick layer actually will be formed on the membrane surface, and then say concentration profile will be like this. Say here, say the bulk concentration will be Cb, and whatever the maximum concentration will be, that is we can say this one Cg. When we can say gel concentration is such a concentration where we should get 0 flux value, or we can say this one there will be no permeate flux. Okay. So, that will be there. So, in that case delta will be here also, we can say this one up to what distance we can say the effect of the solute actually is there, effect of the membrane is there. So, that delta we can say this one, this is the thickness of the say gel layer. After that actually there is no effect of the membrane surface. Okay. So, here actually we can say this one in the gel layer, suppose in this gel layer here the solutes are deposited, we can say this one in gel layer. So, we can say accumulation will be equal to in minus out. Okay. So, in that case accumulation will be like this rho g into dl dt is equal to, we can say this one in will be equal to j w into c, and say out will be say whatever is there, say we can say means it is going back d dc dz. Okay. Or we can say this one, if we keep this one in the same side, then it is like this d into dc dz minus jw into c plus rho g into dl dt, that will be equal to 0. So, let take this one rho g into dl dt is equal to say a constant parameter, because for the time being, because whenever we will be doing the integration across this z. So, we assume that this accumulation will not be we can say altering. So, we can keep this one as this constant, say let rho g into dl dt, that is equal to say let us say k 1. Then boundary conditions will be like this, say when z is will be equal to 0. So, c will be c b, and when z is equal to delta, we can say this one c will be c g. Okay. So, here we can say we have taken this z actually in the opposite direction compared to the osmotic pressure model, because but in that case we assumed that say z was actually 0, then membrane concentration was the solute concentration or dynamic concentration. That is the, we can say this one reverse this one notation is adopted here. We can assume the same thing also, but for simplicity actually we have assumed that these boundary conditions, the reverse also can be true. Like this, in that case d into dc by dz minus jw into c plus k 1 will be equal to 0, or we can say d into dc by jw into c minus k 1, that is equal to dz. Now, we will be doing the integration from 0 to delta, and say it will be like c b to c m. If we take the reverse one also, there will no problem. So, from here we will be getting d by jw into ln cg minus k 1 by jw by cb minus k 1 by jw, that is equal to delta is equal to say we can say d by k. Okay. Now, you see for the gel polarization model, so if we say the concentration of the solute, with this we can say this one flux value jw. So, we have like this, it is decreasing and then it is touching some point, that is we can say this one where we can say this some where this we can say jw will be 0, like this in for different we can say this one k values. So, for different k values we will get one particular point. So, corresponding concentration actually will be giving this C g, or gel concentration is a concentration where we can say the flux value will be 0, or when the complete gel will be formed, then solvent concentration will be solvent flux, or we can say the permeate flux value will be 0. That is why the we will be getting one particular point, this one what is called C g or gel concentration. Okay. Now, this ln C g minus k 1 by jw by C b minus k 1 by jw is equal to say jw by K just by manipulation, and by adjustment we can say this one we will be getting this C g into J w minus K 1 by C b into J w minus K 1, that will be like is equal to exponential J w by K. Okay. And from there actually we will be getting this, we can say just by manipulation we can say K 1 will be equal to J w into C g minus C b into exponential J w by K divided by 1 minus exponential J w by K. Okay. And then this K 1 is equal to say rho g into say d l dt, that will be equal to J w into C g minus C b into exponential J w by K divided by 1 minus exponential J w by K. Okay. So, from here we can say, so now we have this expression, and say we can say we have also this J w is equal to del p by say mu into R m plus R g, that we told that say because the gel layer resistance also plays an important role in case of gel polarization model, means where the solutes are with bigger molecular weight. Okay. And say here, and we can say this one L p membrane permeability will be like this 1 by mu into R m. Okay. And say R g, that will be obtained by, so we can say this one R g will be equal to, we can say alpha into 1 minus epsilon g into rho g into L. Okay. So, that we know this one, this gel layer resistance will be like this, whatever the void fraction is there, and then alpha is this, we can say specific gel layer resistance. Okay. So, from Kozny-Karman equation we will be able to get we can say this one alpha from Kozny-Karman equation. So, we will be getting this alpha is equal to this 180 into 1 minus epsilon g divided by epsilon g cube into dp square into rho g. Okay. And say now we can say this one R g, if we put this this alpha value in this R g, we will be getting 180 into 1 minus epsilon g into again 1 minus epsilon g, that is square into rho g into L divided by epsilon g cube and dp square and rho g, that will go, that will be equal to, we can say ultimately 180 into 1 minus epsilon g square into L divided by say epsilon g cube into dp square. So, that R g actually we will now get as 180 into 1 minus epsilon square into L by epsilon cube into dp square. Okay. So, from there we will be getting now we have got this R g value. So, and R m will be getting from this one by mu into L p. So, we can say this one, the permeate flux value can be obtained from the general expression of like this from del p by mu into R m plus R g. So, from here we will be able to get this permeate flux value. So, next we will be discussing the resistance in series model.